Hello and most welcome to 13777. I would today continue to read an article I began in 1375 by Philip Ball, and I will today finish it, and I will after that continue with my summary of the master and his emissary. Quantum Darwinism is a way to show how things compete. So before, in the superposition, a lot of things are still possible, almost everything. In the collapse or the decision, only one thing remains. So this can in some ways be compared to a sort of Darwinism, a competition. Only one thing will remain of all the potentialities. What do we have after the collapse? Yes, we have the classical world. So if you don't understand or have a clue or a hunch about the potentiality, what is before the superposition, however you think about it, however you perceive it, your understanding will be the classical one. And I would say the classical one is what we refer to when we think about reality, the world, or the world out there. This is what we commonly believe is shared among everyone. But there is something behind. That is the real world of potentialities. So quantum Darwinism, which is quite new, is making a very important point. And that is that from all perspectives, in all measurements, in all viewpoints, the world might look completely classical. But we know it is not. We need to know that. As soon as we forget that, or more commonly, of course, we having no knowledge about it, which is the absolute majority of all people. 99%, 99.9% don't know about the superposition. They healthily, understandably, logically assumes a stable, unchanging, real world and nothing else. Nothing above, nothing below. It is only the understanding coming from quantum mechanics can show to something different. There's no other way. Because of this, all other ways are fake. They're not real. They are wishful thinking. They are imaginations, falsehoods. So you see, there is a quite decisive philosophical point made here. Philosophical, ontological, thinkingly. I will now continue on page 5. I got to the last paragraph. Information overload. It doesn't matter, of course, whether information about a quantum system that gets imprinted in the environment is actually read out by a human observer. All that matters for classical behavior to emerge is that the information get there so that it could be read out in principle. A system does not have to be understudy in any formal sense to become classical, said Jess Riedel. A physicist at the Perimeter Institute for Theoretical Physics in Waterloo, and a proponent of quantum Darwinism. Quantum Darwinism putatively explains or helps to explain all of classicality, including everyday macroscopic objects that aren't in a laboratory or that existed before there were any humans. About a decade ago, while Riedel was working as a graduate student with Zurich, the two showed theoretically that information from some simple idealized quantum systems is copied prolifically into the environment. Riedel said, so that it's necessary to access only a small amount of the environment to infer the value of the variables. They calculated that the grain of dust 1 micrometer across after being illuminated by the sun for just 1 microsecond will have its location imprinted about 100 million times in the scattered photons. It's because of this redundancy that objective classical-like properties exist at all. Ten observers can each measure the position of a dust grain and find that it's in the same location, because each can access a distinct replica of the information. In this view, we can assign an objective position to the speck, not because it has such a position, whatever that means. But because its position state can imprint many identical replicas in the environment, so that different observers can reach a consensus. What's more, you do not have to monitor much of the environment to gather most of the available information. And you do not gain significantly more by monitoring more than a fraction of the environment. The information one can gather about the system quickly saturates. Riedel said. So already has the point been repeated which I made initially. 10 observers can measure the position of a dust grain and find that it is in the same location. Hence, reductionism empiricism is uttermostly proved. That is the truth. That is the reality. In all aspects from that normal take on reality. This redundancy is the distinguishing feature of quantum Darwinism, explained Mauro Paternostro. A physicist at Queen's University, Belfast, who was involved in one of the 3 new experiments. It's the property that characterizes the transition towards classicality, he said. Quantum Darwinism challenges a common myth about quantum mechanics, according to the theoretical physicist Adam Cabello of the University of Seville in Spain. Namely, that the transition between the quantum and classical worlds is not understood, and that measurement outcomes cannot be described by quantum theory. On the contrary, he said, quantum theory perfectly describes the emergence of the classical world. Just how perfectly remains contentious, however. Some researchers think decoherence and quantum Darwinism provide a complete account of quantum classical transition. But although these ideas attempt to explain why superpositions vanish at large scales, and why only concrete classical properties remain, there's still the question of why measurements give unique outcomes. When a particular location of a particle is selected, what happens to the other possibilities inherent in its quantum description? Were they ever, in any sense, real? Researchers are compelled to adopt philosophical interpretations of quantum mechanics precisely because no one can figure out a way to answer that question experimentally.
Excuse me. No, it's okay.
Into the lab. Quantum Darwinism looks fairly persuasive on paper. But until recently, that was as far as it got. In the past year, 3 teams of researchers have independently put the theory to the experimental test by looking for its key feature. How a quantum system imprints replicas of itself on its environment. The experiments depended on the ability to closely monitor what information about a quantum system gets imparted to its environment. That is not feasible for, say, a dust grain floating among countless billions of air molecules. So 2 of the teams created a quantum object in a kind of artificial environment with only a few particles in it. Both experiments, one by Paternostro and collaborators at Sapienza University of Rome, and the other by the quantum information expert Jian Wei Pan and co-authors at the University of Science and Technology of China. Used a single photon as the quantum system with a handful of other photons serving as the environment that interacts with it. And broadcasts information about it. Both teams passed laser photons through optical devices that could combine them into multiply entangled groups. Then they interrogated the environment photons to see what information they encoded about the system photons pointer state. In this case, it's polarization. The orientation of its oscillating electromagnetic fields. One of the quantum properties able to pass through the filter of quantum Darwinian selection. A key prediction of the QD is the saturation effect. Pretty much all the information you can gather about the quantum system should be available if you monitor just a handful of surrounding particles. Any small fraction of the interacting environment is enough to provide the maximal classical information about the observed system, Pan said. The two teams found precisely this. Measurements of just one of the environment photons reveal a lot of the available information about the system photon's polarization, and measuring an increasing fraction of the environment photons provided diminishing returns. Even a single photon can act as an environment that introduces decoherence and selection. Pan explained, if it interacts strongly enough, with a lone system photon. When interactions are weaker, a larger environment must be monitored. A team led by Fedor Yelesko, director of the Institute for Quantum Optics at Ulm University in Germany, probed the state of a nitrogen defect inside a synthetic diamond. By monitoring surrounding carbon atoms, their findings confirmed predictions of a theory known as quantum Darwinism. The third experimental test of quantum Darwinism, led by the quantum optical physicist Fedor Yelesko at Ulm University in Germany, in collaboration with Zurich and others. Used a very different system and environment. Consisting of a lone nitrogen atom substituting for a carbon atom in the crystal lattice of a diamond. A so-called nitrogen vacancy defect. Because the nitrogen atom has one more electron than the carbon. This excess electron cannot pair up with those of neighboring carbon atoms. To form a chemical bond. As a result, the nitrogen's atom's unpaired electron acts as a lone spin. which is like an arrow pointing up or down, or in general in a superposition of both possible directions. This spin can interact magnetically with those of the roughly 0.3% of carbon nuclei present in the diamond as the isotope carbon-13. Which, unlike the more abundant carbon-12, also has spin. On average, each nitrogen vacancy spin is strongly coupled to 4 carbon-13 spins with a distance of about 1 nanometer. By controlling and monitoring the spins, using lasers and radio frequency pulses, the researchers could measure how a change in the nitrogen spin is registered by changes in the nuclear spins of the environment. As they reported in a preprint last September, they too observed the characteristic redundancy predicted by quantum Darwinism. My comment here, it is the redundancy that is the important thing, overlooked before. The state of the nitrogen spin is recorded as multiple copies in the surroundings. And the information about the spin saturates quickly as more of the environment is considered. Zurich says that because the photon experiments create copies in an artificial way that simulates an actual environment. They do not incorporate a selection process that picks out natural pointer states resilient to decoherence. Rather, the researchers themselves impose the pointer states. In contrast, the diamond environment does elicit pointer states. The diamond scheme also has problems because of the size of the environment. Zurich added. But at least it is, well, natural. Generalizing quantum Darwinism. So far, so good for quantum Darwinism. All these studies see what is expected, at least approximately, Zurich said. Riedel says we could hardly expect otherwise, though in his view quantum determinism is really just the careful and systematic application of standard quantum mechanics to the interaction of a quantum system with its environment. Although this is virtually impossible to do in practice for most quantum measurements. If you sufficiently simplify a measurement, the predictions are clear, he said. quantum determinism is most like an internal self-consistency check on quantum theory itself. But although these studies seem consistent with quantum Darwinism, they cannot be taken as proof that it is the sole description for the emergence of classicality, or even that it's a wholly correct principle. For one thing, says Cabello, the three experiments offer only schematic versions of what a real environment consists of. What's more, the experiments do not cleanly rule out other ways to view the emergence of classicality. A theory called spectrum broadcasting, for example, developed by Paweł Horodecki at the Gdansk University of Technology in Poland. And collaborators attempts to generalize quantum Darwinism. Spectrum broadcast theory identifies those states of an entangled quantum system and environment that provides objective information that many observers can obtain without perturbing it. In other words, it aims to ensure not just that different observers can access replicas of the system in the environment, but that by doing so, they do not affect the other replicas. that too is a feature of genuinely classical measurements. Horodecci and other theorists have also sought to embed quantum Darwinism in a theoretical framework that does not demand any arbitrary division of the world into a system and its environment. This is, of course, the same thing with the landscape problem, the form and content problem, signified and signifier, and so on, my comment. And it's an arbitrary division, most pertinent here. But just considers how classical reality can emerge from interactions between various quantum systems. Paternostro says it might be challenging to find experimental methods capable of identifying the rather subtle distinctions between the predictions of these theories. Still, researchers are trying, and the very attempt should refine our ability to prove the workings of the quantum realm. The best argument for performing these experiments probably is that they are good exercise. Directly illustrating quantum determinism can require some very difficult measurements that will push the boundaries of existing laboratory techniques. The only way we can find out what measurement really means, it seems, is by making better measurements. That was the end of quantum Darwinism. Even though the solution is not clear or not 100% proven, the background is clearly depicted. What we do know, and what is foundational in the best proven theory ever of science, is that we have multiple states in a before position, and after there's one single position. What they are debating is, how does the transition work We know it works, but rather is what is the working principle. This goes to show wherever you look, in whatever method, measurement, laboratory, under whatever circumstances, your predictions will prove the classical model. And this we've been knowing all the way. This is an important repetition of that understanding. You can go to the moon, you will only find the classical reality. We know that to be wrong, but this can only quantum mechanics show. And I think that needs to be put in the foundation. And for those of you listening and seeing these lectures, this will be extremely helpful in understanding quantum perception, as we are reading parallel here of the author Stephen M. Rosen. This is very helpful, and this is a far cry from not misunderstanding, but oversimplification or inability to go deeply into the problem, and you get the idea that decoherence, it is what causing the classical world. No, decoherence is an acronym. Okay, put it here. Decoherence is an acronym, so to speak, for a very, very...
Nothing happened, so let's continue.
Decoherence, well, I have to tell you, this is maybe one of the few times, or last times, I have to struggle with these wires. Starting next week, I will be able to use the wireless.
This is Darwinistic pathology.
Decoherence. Very often used and misunderstood in a way. I would say it's too complicated to be out into the public, and it's used nowadays, and then I'm going to put it into maybe something like this. It should be double ones. It is used to say we can ignore. You need to raise that one and keep it still. We need to keep it still with 2 hands, please. We need to take away quantum mechanics on a higher level. This is how decoherence is used. But as you see here, the quantum reality, as I use the word reality, it is the reality. And we can only know that from the exploration, the discovery of quantum mechanics. Decoherence does not take away quantum mechanics. It doesn't make this world more normal. It's not even connected to that sort of thinking. Similar to this misunderstanding, or well, it's not a misunderstanding in the common sense. It is more of not being able to penetrate what it means correctly. And to be able to do this, you need to be a scientist of high degree. So better to cut it out completely, decoherence. better to think of quantum Darwinism as a tool in understanding why we have a classical world out there to our senses, to our measuring devices, in every laboratory and in research reports. It doesn't mean that quantum mechanics disappears. On the contrary, it remains the foundation for reality. Please hold both hands. It does not, so to speak. There is another way of explaining this is, do not think of the last state, the state you see, as being number 1, 2, 3, or 4, or up to a gazillion of the previous state. Before, it is completely superposed. There is nothing like a classical world in the before state. The second point that Ball makes is, well, that goes into the very foundation of what is quantum Darwinism. The idea of all these things, we don't know about them, we can never know about them, but maybe they are interacting in a sort of competition, and one is winning. And that analog is of course coming from biological Darwinism. Take for example the finches of the Galapagos Island, the ones that fired up Darwinism as such by Darwin himself when he was there, visiting with the HMS Beagle all those years ago. Here he saw that on the different islands there have been some sort of competition and adaptation. So Ball's and the second leg of the whole thing is that there could actually be some sort of competition between the different unknown states. We will never know them, but one is winning. So it's a way of explaining why we have a classical reality. It's one way. There are other ways, but we know, and this is the first leg, so you don't forget it, I repeat it once more. We know this to be the case. Very important. Only that knowledge can sort of question the classical reality. Maybe you need to hold both of them until I take it. So keep it. And I put this on you. Oh, hold it, hold the hand.
Okay, now you have to hold it with both hands.
That's
Let
it.
me.
Give me a second here. I need to put you into the...
Hello, hello, hello. I'm Darwin. No, I'm not. Okay. Let me go to Penrose, and we have two Rogers. So when he had his 19th birthday, he had made an analogy. He said that he had gone to a tennis match where there was Roger Federer, around the Roger, and he said that, I'm now paraphrasing, that Roger Federer was, so to say, creating reality every time that he smashed the ball. Okay, so now I would like to, this is my own interpretation, apply quantum Darwinism on this analogy. Okay, so let's say that we have here a tennis plan, okay, and here we have the audience. We can even think Penrose himself here. I apologize for Penrose if he would ever watch this. But okay, we have Penrose here, and we have here Roger Federer, and his adversary here, So let's say now we put, let's imagine like we are Penrose here, or whoever is in the audience, and there is a game. We could call it a fight, Darwinian fight. So only the best survives. Darwinism works here if you because it's only one can be a winner. So it's the best survives. So this is from it's both from the viewer's standpoint, but also from, of course, from tennis players' view. But only one can survive, and so far so good. But it's more complicated than that. So you have the ball coming, so it's like a superposition because Federer has to, so to say, he has the ball. He cannot calculate in advance because the ball is far too fast for him. So in some way he has to have it in his body, so to say. He has good feeling, so he has to, so to say, it's difficult to imagine. But then, according to Penrose, if I understood him correctly, he creates reality every time. So he has taken inside all the room, all the space. So he's one with the space. And we could think about entanglements. This kind of entanglement, he can feel the ball. So it's only not local reality, like he is Roger here. So he's one also with the ball, we could say, perhaps, in one way. And he has several options. Well, all these options collapse in a superposition. So this is perhaps in one way I would think about it. And then if we would like to use, you said that this word redundancy was important. So redundancy, if I understand it correctly, you said that so Roger has several options in one way, because the ball can come from here to left or right. So there is a redundancy of options. Redundancy is a negative term, but you could say he has wealth of options.
Well, I think redundancy is a correct word. It doesn't carry anything negative.
No, it's not. Okay. Anyhow, okay. Redundancy, he has several options. That is what is meant with redundancy in this article. So he has a lot of options, 1, 2, 3, 4, because left, right, up and down. Infinite of, and decoherence, if you want to use it. So decoherence is that is perhaps another word for Schrödinger's what to call it, his uncertainty principle, in the say that everything's disorganized. So it's uncertain because the ball can come from here, left, right. But they are really the same terms for the same thing. Uncertainty. That is because the ball can come from here and there.
Oh.
And but you can still call this Darwinism. It's already depends on the label. If you want to give a label, okay, counter Darwinism, but it's so do you want to add something, Hans, to this, my explanation or understanding?
Well, I can just say it's perfection, Kalle. Thank you very much. It's exactly what this is about. I can't even think of anything to add. But maybe to make things even clearer, this is very clear, very good. Think about all the positions, the ball, the racket, his body, his eyes, his hearing, his proprioception. It is pure infinity. It is quantum superposition, and this is what Roger Penrose meant. It will collapse when he hits the ball. And for us viewers, Penrose is sitting in the audience, there will be like one classical thing happened. And all the people in the lecterns, they will agree. What happened? This happened. This is the after. What Roger Penrose was pointing to was the fantastic before. And to make it even sharper for you who are mathematically inclined, if you are very persistent, which I was once upon a time, with the classical take, you would say there are a gazillion options, but they are not infinite. There are some sort, theoretically, potentially, never to be happening ever, but still, in a manner of speaking, exhaustive, that is non-infinite. No, we know them to be infinite, and that is a very important extra sharpness that you can sort of think about. Excellent depiction, Kalle. Thank you very much. It was clear, nothing to be added. It was clear as the sky was this afternoon. Thank you very much, everyone, and thank you for your patience. You can put pause there, actually.